So hi everyone, so I'm Florent Robert, a French PhD student from the Université Côte d'Azur. So I'm going to present our work on our task-based methodology to characterize immersive user experience with multivariate data. So lifelike experiences in virtual reality are very promising. They allow us to create application and research domain with personalized lifelike trainings and scenarios. There are many works in the XR domain which create such training experiences, such as the Clifford work, which create a stress-inducing VR experience for firefighter, or the work of Lang, which create experience for car driver, which based on the attention of the user, detect the bad habit of the driver and generate some personalized experience. So user behavior and performance analysis in such experiences is very important, as it allows to create better personalization and to provide some personalized guidance based on the user difficulties and needs. However, such analysis is pretty challenging. In such lifelike scenario, we trigger lifelike also emotion and reaction in the user. So we have to record more information on the attention of the user, the motion of the user, some physiological data about the user. And the context of the VR is pretty complex also. So we have to record with what the user is interacting with, the state of the environment, and what are the tasks the user is currently doing. And there aren't many work on how to properly do this kind of analysis in the VR domain. So we propose a methodology aiming to characterize behavior and performance for training experiences, and while being able to use already existing multimodal VR datasets. So this methodology is in 3 steps. The first steps consist of aligning the behavior and the contextual data of the experience in order to provide a fine-grained analysis of the user behavior. The second step is to define the performance baseline, the point being to be able to define the expected performance for each task of a scenario using some HCI methodology, notably the GOMS and the task model that I will talk a bit more about later. And then the last step is to characterize the user behavior based on the observed performance. So to exemplify the usage of this dataset, we used a dataset from a study we made in our previous work, in which users were placed in a simulated exterior environment in which they have to do some diverse interaction, and they have to cross a road with a simulated car traffic and simulated traffic light states, which some of you maybe may have done. So in this dataset, we collected a total of 960 scenarios, and we focus for this work or analysis on the task to cross the road only. In this study, we recorded many data. We have the motion capture for the motion data. We have for the physiological data, the skin conductance and the heart rate. And for the attention data, we have the eye tracking. And we also record the whole context of the environment. So with what the user is currently interacting, what is the state of the environment, what is the position of the user. So this is a very rich dataset of multivariate data, and analyzing such dataset can be quite demanding, which is why we propose this methodology in 3 steps, as I explained. The first step is to align the behavior and the contextual data in order to build a synchronized multivariate data. It can be seen like this. So on the first line, the 3 first line are raw data of behavior. So the first line is the EVA, so it's the electrodermal activity, giving us a view of the emotional arousal of the user. The POR is an attentional metric, giving us the point of regard of the user in the environment. And the chest in degree is just one of the many motion data contained in body motion data. And all these data are, as you can see, synchronized with the context that you can see at the bottom. You can see the task that the player is currently doing. So go outside, cross the road, take the box, and cross the road again. And here already we can see a clear link, which are logic, between the raw data and the context. So if you look at the point of regard, you can see some big variation happening in the middle of the task cross the road, which is logic, as the user have to look at the traffic light and look at the car before crossing the road. So once we have this data frame synchronized, we can work on the definition of performance baselines. So in order to define precisely what we expect the user to do in order to consider the task a complete success. So again, for the task cross the road, we identified 3 performance components for this task. The attention component, which is the important element that the player will have to look at during the task. The decision component, which is the decision that the player will have to take during the task. And the efficiency, which is just the time to finish the task. So for the efficiency component, we used a methodology based on GOMS. So GOMS is quite a well-known methodology in HCI domain, so in a human-computer interaction domain, where each low-level task is assigned with a duration. So for example, you can see on the table that double click, for example, is considered to take 0.2 seconds. This way, by combining the different duration, we can define the expected duration for a more complex task. So for example, for a task which asks me to think about something, move my hand on my mouse, point somewhere and click, I can expect this task to take a total of 2.9 seconds. So based on this methodology, we built our own table using also some work that already exists for virtual reality. And we defined, for example, that we can expect for a task to grab an object in virtual reality to take 2.6 seconds. And based on that, we can define for a task cross the road that the user first will have to wait for 1 second for the audio instruction. Then they will have to wait up to 8 seconds for the traffic light to turn to green. And finally, they will have to walk physically 5 meters at a speed of 0.9 meter. So we expect them to finish this task in 13.5 seconds. Now, for the attention and the decision component, this time we took a task model approach. So a task model is a model that segments a task in a list of lower level tasks. For example, here you can see for enter the PIN code, we have to ask for the PIN code, then decide to enter the PIN code, remind the PIN code. So there are multiple small low-level tasks that we need to perform in a given way. So we applied this to our context, where we created, here you have a visualization of a very simple task model focused on the cross the road task. So here you can see that for the task cross the road, we expect the user first to wait. Then they will have to look at car and look at traffic light. Then they look at the state of this object. Is the traffic light green or red, and is the car stopped or not? If for both it's red, then they will wait a bit more. And once finally the car is stopped and the light is green, they can cross the road. So with this, we can define that the attention component is basically look at car and look at traffic light. And for the decision component, if the user cross while the traffic light is red, then he took a bad decision. With this, we defined the performance component baselines that we need to define if the cross the road was a success or not. So the user need to cross the road in a total of 13.5 seconds. He need to look at the car and the traffic light before crossing, and they need to cross the road while the light is green. So performing the task without achieving the baseline is considered a task misstep. So if I cross in 20 seconds, I do an efficiency misstep. Now that we defined precisely what are the performance we expect for the task, we can then, well, first we can visualize a bit the data. So here you have a visualization about the efficiency performance visualization. So each row is a user which perform a scenario. So here you have the 40 users who perform the one similar scenario. The scenario asks them to go outside, cross the road, take a box, cross the road again, and place the box on the table. When the task is above the baseline value of efficiency, then it's framed in black, which means that they did a misstep of efficiency. So you can see that most of the tasks framed in black are the green one and the purple one, which are the cross the road task. So that's the expected result. Now that we have this, we can go on the characterization of the user behavior. So we have our user performance to know exactly what we expect from the user and what is their behavior and the context. First, a little overview of the presented data. So again, this analysis is focused on cross the road task. We have on the 960 scenario, a total of 630 missteps observed. The majority are attention misstep. So people often don't look at car and light. It's French, I guess. We used a free metric for this analysis. We used a motion metric, which is the copy, the center of pressure inclination, a physiological metric, which is the electrodermal activity, and an attentional metric, which is the gaze fixation duration. The point here being to use 3 different types of metric in order to display a bit the possibility that we have with the methodology. So we can perform 2 types of analysis. First, we can perform an analysis on the scenario level. So here we grouped all the user data for each scenario. So you can see on the graph, each row is a scenario. And for each row, there are 2 boxes. There is the green boxes, which correspond to the data of the user who did no efficiency misstep. So that's the person who crossed the road in time. And the red box is the person with efficiency misstep. So they were too slow to perform the task. And we can see already pretty easily that there is a stronger copy on efficiency misstep group, which basically means that people who were too slow at crossing the road were also people with a stronger body inclination. So this is an interesting first analysis to observe the relevance of a metric for a given type of task. A second analysis that we can do to go even further, don't try to read the table yet. This time it's an analysis on the user level. This time we analyze the user individually, but we group all the data for each user individually. And we select all the users that show a strong correlation between a type of misstep and a metric variation. So we selected only users which show a p-value under 0.05, and with at least 10% of missteps in order to have a good amount to compare between the group misstep and the group non-misstep. So with this, we have this big table. What does all this mean is basically here we have 2 users. These 2 users did 54 and 42% of misstep in all the tasks they did. And we can see a variation of -29 and -22. What does that mean is basically that all these users, when they were doing an efficiency misstep, they had their copy, so their body inclination, that was stronger. So this way we identify a user profile that can be in link with a common error. We have other profiles that are different also. Here, for example, we have 2 other users who did 25% and 15% of missteps, still on efficiency. And this time we can see that on the gaze fixation duration, one of them have slower, shorter fixation duration, and one have longer fixation duration. So here we have two different profiles for a same efficiency misstep, for a same type of misstep. So this analysis is interesting for multiple points. First, it opens more in-depth analysis as we can identify some user profile and make a link between a behavior and an error, which help us to investigate on the potential user difficulty that can exist to perform a task or a scenario. And finally, all this can contribute to create a more personalized experience as we are able to identify when an error happens and what behavior can be linked to this error. So to conclude a bit of discussion, this methodology allows us to segment tasks and define performance baseline. It allows us to observe finally the user performance and behavior, and finally characterize the user behavior based on their misstep. This methodology aims at being flexible by using any type of multivariate data type, and is reproducible for any VR dataset as long as they propose a synchronizable context with the behavioral data. There are, of course, some limitations. First, we can't claim causation on the data. Like, for example, we can't say if the people are more inclined because they did an error or they did an error because they are more inclined. So for this, we will need more post-study and post-questionnaire. This analysis was focused on the task across the road only. It could be interesting to look at different type of tasks to see what we could get. It could be also interesting to go more in depth on the analysis of behavior by using multiple behavioral data to see if we can create more precise profile. And finally, the amount of open dataset in VR that exist are not in that big number. And it will be interesting in the future to have more of such dataset to open more possibilities for behavior analysis in VR. Thank you for your attention.